So let's talk now in terms of coupling. I want to give us a few more coupling constants and then set the stage on this. So let's talk about CH coupling. We talked a little bit about this before. And, you know, a typical sp3 carbon-hydrogen bond, so the attached hydrogen, the J1 CH is on the order of 125 hertz. In other words, if you have, say, ethane, your J, and this is from a table in Silverstein that I gave you in the handout, your J is about 124.9 hertz, right about 125 hertz. Cyclohexane, these are all examples of sp3 carbons, 123.0 hertz. All of this is in the table. The main point, remember I talked last time about hybridization being one of the factors that affects your J value. The main point is these carbons here, these sp3 carbons, have a certain amount of S character. sp3 means you're roughly 25% S and 75% P. As you put in more S character and go to sp2, your J1CH now increases. It goes to about 160 hertz. And so, and again, this is right from the table that I have in the handout. Ethylene is on the order of 156.2 hertz. Benzene on the order of 159 hertz. And I want to take a look at a few other ring systems and acetylenes. And then I want to talk a little bit about some practical implications of this. So we've already talked about small rings in the IR spectrum. And, you know, one of the things that I think is so cool when we talk about small rings is in the carbonyl stretching frequency, we can see the implications on the hybridization, on the strength of the CO bond. Small rings have a stronger carbonyl stretch. And that's in part because they're using more P character in the ring and more S character in the CO bond. And we see a similar thing in the J1CH, where we're using more P character in the ring, so there's more S character in the CH bonds for a cyclobutane or a cyclopropane. So the coupling constants, the CH coupling constants in cyclobutane butane are on the order of about 134.0 hertz. And for cyclopropane, your J1CH is on the order of, I guess since I'm giving a specific example, 161.0 hertz. And then if we go one step further and we go to alkynes, so sp hybridized, now we're at about 250 hertz. For example, for acetylene, it's 249.0. All right, so the implications of this are important. So in spectral techniques, in techniques that require or based on a typical CH coupling, things like alkynes may behave in ways you don't expect them. In other words, because a technique like DEPT or HMQC, which we're going to come to, is based on a typical CH coupling that normally for everything else would be on the order of about 125 to 160 hertz. So you can maybe pick an average value and kind of split the difference and say, okay, we'll use 140 hertz as an average J1CH. That works very badly for alkynes. For chloroform as well, you notice when we talked about CHCl3 and the one bond coupling, and I said it was 209 hertz. So I'll just say for the implications that alkynes and other compounds with large J values J1CH values, I suppose, may give what I'll describe as erratic, only because I mean that you wouldn't expect it, erratic results in the depth and HMQC experiments. And I'll just say which assume typical CH couplings. All right, now the reason this is important, and I think we finally removed this example from the homework problem, the reason this is important is that means if you have a compound with an alkyne in it, you may not see what you expect. And we had an example in the homework problem at one point of, I think it was an HMQC or a het core experiment, and people could never find the alkyne group and got all confused. And so it's a real situation that comes up. Thoughts or questions at this point? So what I said here is simply implications, alkynes and other compounds with large J1CH values may give erratic results in the depth and HMQC experiments, which assume typical CH couplings. All right. So I want to talk briefly about J2CH couplings and J3CH couplings, and again, give the practical implications. All right, so I already talked sort of in general terms about 2 and 3 bond heteronuclear couplings. And so specifically, let me give some values here. J2CH is typically small. A few hertz. And it's sometimes negative, which doesn't have particular implications for what you observe. So I'll put that in parenthesis. And J3CH typically is on the order of 0 to 10 hertz, and it depends on the dihedral angle. Now, the implications of this are also interesting when we come to the 2D experiment called an HMBC coupling or an HMBC experiment. Not all J2CH coupling, J3CH couplings or J2CH couplings end up being seen in an HMBC experiment. And at least for J3, I'll say because the J3 depends on the dihedral angle. And that's going to make more sense to you later when you start to use these experiments to help interpret data. All right, so I want to go briefly to our handouts. So I'm going to share my screen again. So here are some typical values that I think we, that largely I've shown here already. Oops, where is my stylus? So we see our SP3. And we see a variety of different ring sizes. We see our cyclopropane here. We see typical SP2 examples, typical SP examples. And I guess here in this table, we have a few more examples. I just pulled out some heteronuclear couplings of various sorts here. All right, I think at this point, what I want to do is show us an example. And the example I'll show you is on the final page of your handout. So just give me one moment here. Oh yeah, I guess I have one more thing I want to talk about. All right, so I guess maybe the final thing I'll mention in regard to CH coupling for right now is the way in which we see a C13 spectrum. So if you look at a regular C13 NMR spectrum, let's say you're looking at the spectrum of ethanol, you would see, say, a line at 57 ppm, and you'd see a line at 18 ppm. And those lines would be singlets. And that's because you're regularly running your C13 with proton decoupling. What that means is while you're acquiring the C13 spectrum, you are, and let's say that's at 125 megahertz, you're irradiating the protons in the molecule at 500 megahertz, and that irradiation is flipping their spins very rapidly. So the carbons don't see the attached protons or any of the adjacent protons as spin up or spin down. It sees an average, and all of your carbons come as a single line. And that's very good because it means that all of the area of the peak is concentrated into a single line. If you were not H1 decoupled, then your peak at 57 would primarily be split by the two attached hydrogens. So it would be like a triplet, but you'd get additional splittings. You'd get J2CH splittings from the hydrogens of the methyl group. And so instead of appearing as a singlet, you would appear as a triplet of quartets. And for the peak at 18, instead of appearing as a singlet, you'd see coupling to the three attached hydrogens with a big J value of about 125 hertz, and then coupling, two-bond coupling to the adjacent hydrogens with a few hertz. So this would appear as a quartet of triplets. And all of the peaks would be way shorter, and your spectrum would be way noisier because your signal peaks wouldn't arise that much over the noise. And I hinted before that your H1 decoupling not only goes ahead and concentrates your peak into a singlet, but you also get a nuclear overhauser effect. That's the perturbation of those very small differences in population by the larger differences in the proton population. So your singlets end up being about twice or so taller than they would otherwise be. All right. Thoughts, questions at this point? So I want to take us on to a final example here that I think is fun and I think is sort of cool to wrap our heads around as sort of a capstone on this. All right, so I went into the Aldrich catalog, and you can download lots of NMR spectra, and I wanted something that provided a nice example of molecules with various heteronuclei in them and various other sorts of nuclei. So I pulled this example of a Horner-Wadsworth-Emmons reagent, a reagent that's like a Wittig reagent that contains two C13s in the phosphorus. So it contains a C13 acetate unit with the central CH2 and the carbonyl as a C13 carbon, pure C13 carbon. And we have the spectrum over here, and we have the carbon 13 NMR spectrum up here. And because all of the other carbons, the ethoxy groups on the phosphorus and the ethoxy group on the ester, are natural abundance, they are very short. But in the carbon NMR spectrum, we see some tall lines. And what I want to do is work through all of these lines to figure out what our respective coupling constants are. So if we start at the proton NMR spectrum, we see a really interesting pattern over here for the CH2 group, right? These are our ethoxy groups on the phosphorus and the ester are off on the side at about 4.2 and about 1.3 ppm. But then at about 3 ppm, we see this pattern here. What is the pattern that we see? What is the pattern that we're looking at over here?
Doublets of doublets of doublets.
A doublet. So this is, run that by me again.
So I think it's 4 Ds or 3. I think it's 3 Ds. Doublet of doublet of doublet.
Doublet of doublet of doublets. So what are those hydrogens being split by?
Themselves and the Ph.D. and the phosphorus. Yeah, themselves and the phosphorus.
So the hydrogens, do they split each other?
If they're enantiotopic, yes.
If they're enantiotopic, no. So they're enantiotopic. If I replace one with a deuterium or I replace another with a deuterium, I get enantiomers, but enantiotopic protons don't split each other. So who are those hydrogens getting split by?
The two C13s and the phosphorus?
The C13s and the phosphorus. So in other words, we have a splitting from the attached C13. We have a J1CH. And then we have another C13, that's the carbonyl over here. So we have a J2CH coupling. And finally, we have a 2-bond pH coupling. So those are the 3 splittings that are splitting those hydrogens. And I went on for this doublet of doublets, and I put a ruler under it. What I did basically was just expand the scale and make it into a ruler with appropriate distance measurements. So how do we measure the smallest J? What's the smallest J?
Between the first and second peak?
Between the first and second peaks, and out of convenience, I'll just go here. And I will go here because that's right on the ruler. And so those tick marks are 2 hertz apart. So the smallest J is 7 hertz. And how do I get the next J for a doublet of doublets?
It's the first to third peak.
First to third peak. So I can go ahead and measure to this peak here. And that's, I think I went a little cockeyed with my line. So I think it's more closer to the 22 hertz mark. So that's 22 hertz. And in this case, now I've cautioned you and said in a DDD, sometimes it can be line depending on the splitting pattern. Sometimes it can be 1 to 4, sometimes it can be 1 to 5, but it's always 1 to 8 minus the others. We could do that. We could say, okay, you know, we're about 159 hertz over here, and we could subtract 22 and 7 from it, and we would get 130. Or looking at this, it's pretty obvious that there is one honking big J. So you know, either way, I can read off of here. And if I read, you know, either way, I'm going to come up with the same answer. That distance is 130 hertz. So in other words, this is a DDD, J equals 130, 22, and 7 hertz. And all the couplings are heteronuclear couplings. Now, I think it's pretty obvious here. If I only had this information, it's pretty obvious based on everything I've been saying about one bond coupling, that our one bond coupling, our J1 CH, is equal to 130 hertz in this particular reading, right about where you'd expect it. And it might not be quite so obvious for our J2 CH and J2PH. And if you remember what I talked about on Wednesday, you might say, okay, J2PH is usually bigger than J2CH, and I just said J2CH is a few hertz, so we probably could just figure, all right, the 22 is the J2PH, the 7 is the J3PH, but we can also get it from our carbon NMR spectra, and we can analyze these lines in the carbon NMR spectrum just as well, and maybe that's a nice way to do it. So if we look at our carbonyl peak over here, and we look at our methylene peak over here, and we look at our peak printout here, we see that each of them is a DD. And remember, on all of your Aldrich spectra, the H1 NMR is 300 megahertz, and the C13 NMR is 75 megahertz. So in our DD for the carbonyl peak, we have a distance of 161. I'll take lines 1 to 3, and that's 166.15 and 165.37. And I take that difference, and it's 0.78. And I multiply by 75 hertz per ppm, and I get 59 hertz. And I go ahead and I take our distance of 1 to 3. And that's 0.08. And so that's 6 hertz. Oops. And so again, our one bond coupling is going to be the biggest. So that's our J1CC is equal to 59 hertz. And this is our J2PC, and that's 6 hertz. And then I can go ahead and we can look at the other doublet of doublets, the CH2. And that's a doublet of doublets, and we get, let's see, 35.74, 33.96, just reading off the table there. That's 1.78. And so that translates to 134 hertz. And then I do the other doublet of doublets, and I get 100 and let's see, I get 35.7 0.74 minus 34.96. That's 0.78, and that translates to 59 hertz. And so our J2 PC, our J2 PC is equal to 6 hertz. I think we got that up here. And then our J1 CC is equal to 59 hertz. And our J1 PC equals 134 hertz. And over here, I said our J2CH is equal to 7 hertz. And our J2PH is equal to 22 hertz. So that's a whole load of couplings analyzed from a sort of a simple and common spectrum here, where we're teasing out the coupling constants and thinking outside of our usual proton-proton coupling. So any concluding questions on the heteronuclear coupling? So the homework set will give you some problems. I don't think any are quite as, shall I say, intricate as this particular example, but they'll give you some good examples in which to think about these types of heteronuclear couplings and their implications. All right, what I want to do at this point is change gears and talk about dynamic processes in the NMR spectrum. And I want to start with a couple of sort of simple maxims, because I think this is a good place to ground ourselves before we start getting into variable temperature effects and so forth. And so what I want to say is processes with lifetimes of greater than, say, 100 milliseconds I'll say much greater than 100 milliseconds. And I'm just giving us some ballpark numbers. So I like the idea of 100 milliseconds, 10 milliseconds, 1 millisecond, 1 second. So I'll say processes with lifetimes much greater than 100 milliseconds are generally slow on the NMR timescale. And I'm going to put the NMR timescale in quotation marks because there's actually multiple NMR timescales for different types of processes. But I think most people would think about what is the NMR timescale for a dynamic process. There are different timescales for relaxation. The NMR timescale we're talking about here is essentially dictated by the uncertainty principle. And at the other end of the extreme, I'll say processes with lifetimes much less than 1 millisecond are generally fast on the NMR timescale. And again, I'll put that in quotes. And of course, these processes are going to occur at different speeds at different temperatures. So we're going to use temperature as a way of modulating the processes to go from this very fast time scale to this very slow time scale, or in reverse from this very slow time scale to the very fast time scale. We're also going to be talking about energy barriers, and I'll give you some general rules. Processes with an energy barrier greater than 20 kilocalories per mole are generally slow. And processes with an energy barrier less than 10 kilocalories per mole are generally fast. So an example of a fast process would be rotation about a carbon-carbon single bond, like the rotation about the single bond of ethane or butane, the central single bond. A process with a very high energy barrier might be, say, racemization of a chiral phosphine, where phosphorus is chiral and it doesn't racemize, or a chiral sulfoxide doesn't racemize at room temperature. But we're going to look at sort of the interesting intermediate ranges. And I'm going to start us with something that's slow at room temperature, but then we're going to see how this process can become fast on heating. And I'm going to start with a very simple example. And we'll start with simply diethylacetamide. It's a nice example. People often use amides such as dimethylformamide or diethylacetamide as a sort of archetype for dynamic processes in the NMR. So let's take diethylacetamide. And we've already talked about the IR spectrum. We've talked about this nitrogen donating its lone pair into this carbonyl. So in an amide, that nitrogen is not an sp3 nitrogen like an amine. It's much more like an sp2 nitrogen because of hybridization with the carbonyl. And we see two ethyl peaks. We see two sets of ethyl peaks in both the H1 NMR and the C13 NMR. At least at room temperature. If you heat it up very hot, you won't. And you can think of it in this way. You can think of it, imagine we went ahead and we put a star on one of these ethyl groups as sort of a thought experiment. And we envisioned a process of rotation by which we rotated about this central bond. And if we did that in our thought experiment, we would have two different variants, But the interconversion, the time for the ethyl group to swap from here over to here is slow. In other words, K forward and K reverse in this case are going to be the same value because these two are equivalent. It's not always the case, but this process doesn't occur rapidly. And of course, we can explain this in terms of resonance, where the amide is not just this structure, it is a mixture of two resonance structures. In other words, that's a really bad way of explaining it. So let me start over here. This structure here is an incomplete representation of the structure of diethylacetamide. Even though we only draw it this way, typically, in the back of our mind, we keep in mind that a more complete picture that reflects the electronic structure of the molecule is not purely a double bond to the oxygen and purely a single bond to the nitrogen, but some of a double bond to the nitrogen and a single bond to the oxygen. In other words, it's 80% this and 20% this, or 70% this and 30% this, and that is a more complete picture of the molecule. And that's why rotation is slow. And we can look at an actual example, and I'll pull up the spectrum of diethylacetamide. That's on today's handout.
James, may I briefly interrupt?
Yeah.
Right now it's 9:45. So in order to get everyone to their exam, we need to finish in 5 minutes.
Perfect. All right. So here's our spectrum of diethylacetamide.
Also, you're not sharing your screen.
Oh. Still not sharing it. All right, here's our spectrum of diethylacetamide. And you'll notice that we see two triplets over here for the two ethyl groups. And we see two quartets here. You can see they overlap a little bit. So we go 1, 3, 3, 1. And then for the other, we cross over and we see two quartets. And in the carbon NMR, for the CH2 group, we see two lines. And for the methyl group, we see two lines. In other words, you have two chemically non-equivalent ethyl groups in the molecule. All right, I think this is probably a good point to stop because we have the exam coming. Actually, let me give you, yeah, this is a good point to stop, and we will pick up on Monday morning talking about what happens as we go from a low temperature to a high temperature. So I'm just going to preview. This is a simulation, and then I'm just going to preview a real example where on the very last page, you can see another amide with something very interesting going on. As we go from room temperature, you see two ethyl groups, and then as we warm it up, and we see that they coalesce. So we're going to pick up with that next time and talk about the energetics of the process.
James, can I ask a question?
Yes, please.
So Which one would be the more de-shielded one? Is it the one that'd be metal side?
Great question. So in general, the carbonyl shifts groups downfield. The carbonyl has its own ring current. So I would typically expect this ethyl group to be slightly more downfield. In other words, higher chemical shift. And this ethyl group to be slightly more upfield. And later on, when you get to the nuclear Overhauser effect, you're going to be able to test this experimentally because your methyl group would be near to this ethyl group, or specifically the CH2 group, and you would expect to see what's called an NOE between them. And we'll talk more about that later. And this methyl group will be far from that ethyl group. So you'll be able to determine that empirically.
Thank you.
You're welcome. Other questions? All right. I will wish you the best of success on your organometallics exam, and I will see you on Monday. Those of you who wish are welcome to join me for my office hours at 5 o'clock, and I'm going to do things the same way, where if there are specific questions, I'll be delighted to talk, and then I'll also be delighted to just leave my video open and step off and do other things and let people work together in groups. And I think if you don't want to join me tonight, I think you also are welcome to join James on Sunday night at 5 o'clock as well. All right, bye now. Good luck to you.